This slide.
All right, very good. The recording has started. So look, let me first say welcome everyone. Looks like the numbers keep climbing. This this is a great way to start our second year of CR2C2 seminars. And I'm personally, I'm very happy for the University of Alabama to have kicked that off. I'm also happy to turn this over to Dr. Alex Hainen, a good colleague and friend here at the University of Alabama. He's been here about 10 years, did his graduate work at Purdue University and undergraduate work in Michigan or Canada. It was kind of right on the border there. And Alex, like I said, Alex has been here about 10 years. He has made an undeniable impact on traffic signal systems and traffic signal operations here in the state of Alabama. You're going to hear some details about that, maybe some impacts and some inner workings of some of the projects. And in addition to that, I will say that I've been in this business a long time, and I have never known anyone to love traffic engineering as much as Alex Hainen. So with that, Alex, show's yours.
Thanks, everyone. Thanks for being here and let me talk with this group. This is my first interaction here with the UTC, so I'm excited to share, like Steven said. Funny that he actually hired me 10 years ago, so this is kind of a summary of some of the bigger components that we've done, particular in coordination with rural and suburban applications. There's a lot of other research that we've done otherwise, but I do want to make sure up front here to acknowledge that this is a huge team effort. This has just been a lot of people that I've been very fortunate and blessed to work with over the years, all the way from my advisor there in the top left, all the way to my grad students who are getting ready to graduate this semester. So it's fun to see that and just the team that goes together behind this. So with that said, I'm going to jump right in and kind of give you a highlight of probably the first, I want to say maybe 3 to 4 years of getting things up and running here around Tuscaloosa. So I came here 2014. And my background was signal performance measures. This slide is funny. If y'all look at it, it looks pretty simple. And really, this was the setup from back in the day, and it's changed a lot over time. Signal performance measures, what we were doing was we were enabling data to be taken from the controllers on the software side to look at every input, output, decision, everything that the controller was doing to the nearest tenth of a second. That has been extremely useful data. We've seen very wide adoption. In the lower right-hand side, I'm proud to say that I got to be involved with the creation of the ATSPM platform. I went out to Utah in somewhere around 2011, 2012, and 2013, working with that crew out there. Mark Taylor, Shane Johnson, Jamie Mackey. This was all stuff that we worked on, and it grew into a national, into everyday counts a few years ago. What was really nice, and this is kind of a funny joke for me, is as I was working on this, it became an FHWA product right when I came to the university here. So the first version of it, this was the open source FHWA variant that we have. And I'll show you the new one that we've got and some of the other things. But you'll also notice, and this is kind of funny, like Steven said, my undergrad was Michigan Tech. I went to Purdue. The first open source version was blue and orange. So we've had to walk a few lines on some of the colors on this. But one other important note on the left-hand side, also cool and unbeknownst to me at the time, was that M60. That was a new controller from Siemens that came out in 2013. I saw one of the early variants of it unveiled to Indiana Department of Transportation, and that's what really set us up here to get us going. What is important here on this slide also is down in the lower right where my cursor is, that was the fiber network that was in Tuscaloosa. A lot of the work that I do these days involves either getting data, seeing what's happening, or components communicating with one another, as you'll see. It was very unusual that Tuscaloosa did have an existing fiber network. So we've evolved that, we've added to it, and it's something that's a great asset that we rely on. However, you do see some other technologies such as radio and cellular that we were able to work with. So this is very old. This was the starting point. This is where it started. On the ATSPM part, we had a colleague from Oak Ridge National Lab here this week talking about smoothing traffic, and that's what we're after too, is we're trying to look at arrivals on green. Steven has a hand up. Steven had a hand up. Okay, I'll just keep going here. Sorry about that, Steven.
Sorry, that was an accident.
Oh, okay, got it. All right, I was perfect. So this is one of our corridors here in Tuscaloosa. Percent on green was one of the performance measures that we used very early on. It was very, very powerful for us. So we worked on a lot of coordination projects with the DOT. And for me, this was my first few years working with DOT engineers here in this state. That is a key relationship that I just want to make sure that to acknowledge all of their collaboration. This is something that they kind of took a gamble and said, this sounds kind of weird, but let's give it a shot. And it has grown and grown and grown, which is what you'll see. Um, Speaking of growing here, this was our second version of our TMC, our Traffic Management Center. We didn't have one here in this region. There may have been like a computer that was perhaps dedicated over at one of the area offices. This is the second TMC. We have a new TMC, which is right below me. We opened it up in January. It is 6 times the size of this. So you can see everyone's packed in here. We use this for football, special events, anything. It's a 24/7 operation. We have students go in here. So we just continued building and doing more and more traffic. I see Dr. B has a hand up. Just want to make sure. Dr. B? Okay, I'm going to keep going unless I hear that part. So what really also got fun was working with all the manufacturers on the private side too. This was a pool of fun study that we got to be involved with. That person over there is a great, great colleague, Dan Nelson from Siemens. I think he's at a consulting firm now. But this was something where we were looking at the second generation of that signal performance measured data. I got to work with every other manufacturer of traffic signal controllers, Econolite, Siemens, Peak, Inalite, Trafficware. I'm missing one. McCain also, of course. But they came into our lab. They've been here. This is when my lab was in its younger days. Now it is filled to the gills. The last count, I think we were up over 60 controllers. So it's been fun just working with all the generations of technology and all the folks involved. Around 2021, this is when we really got things pretty well implemented here. We were up to nearly 500 intersections, and we've got conversations going on with a lot of other areas, cities, municipalities to keep expanding this. So this is just the more recent snapshot. It's kind of been mapped into the Algo suite. You may see this logo in the upper right here. So the colors changed again, but as we matured in our operations, that's also what we were able to kind of put this all together and start putting multiple things that CAPS, our Center for Advanced Public Safety. Hopefully you'll hear about them from either Stephen or Mazan. Tim Barnett's on this call. I see him here. So the safety aspect and playing into that portfolio of products that we have for traffic systems here in this state. The other one that we're working on, this one's newer. We've been working on it and tuning it and working and adjusting, is our management side or maintenance side for detection. We do a lot of sensing technologies that you're going to see later on in this talk. That's probably my most exciting area that I can't wait to share with you towards the end of this. We'll go through the connected vehicles and where we step through on that part in some of the rural suburban applications. But then we'll also talk more on the sensing and how this is changing. And we're really looking at some cool mapping, placing vehicles and things like that. That set the stage for you for really, like I said, probably the first 5 years, maybe a little longer, that some of those last parts there. But now I want to talk about connected vehicle. I just want to make sure that everyone knows here, I don't pretend to be an electrical engineer, a software engineer. At the end of the day, my favorite thing is to go out to an intersection and look at the traffic aspect of this. There's a lot of lessons learned that I'll talk through on some of the radio side on this. I'm glad I get to work with electrical engineering colleagues and folks who are better at getting under the hood on some of these. I don't want to lose sight on really the traffic side and what are we trying to do at intersections, on corridors, on whole systems. And so I will probably underwhelm or underimpress what you might be expecting on this connected vehicle side, but I'm proud of what we've got here. I think there's a lot of smart stuff that worked. And I think we're kind of just actually hitting sort of a second stage of this. I shared a video link at the beginning of this chat that gives an overview of where we partnered with Applied Information. That has gone so well, and I'll talk more about that here. But first few slides gave you the setup of the SPM, the communication backbone. Part of the upgrade was putting modems in there. I'll talk about that in a moment. But 2017, there's a real fun story on how this ended up happening. We went out and deployed the first connected vehicle radios in this state. They were DSRC radios back in the day. I'm guessing everyone probably knows that term, but it's also been sunset now. So we're on to sort of the next stage with CV to X coming around and trying to learn what we're doing there. We've got some pretty cool applications and research that we're working on here that I'll talk about later. But this was the first connected vehicle radio that we hung. This was part of an effort where we had a DOE project that went really proposal really well received, but they said you don't have a connected vehicle deployment. So we said, let's go ahead and do this. And we got behind it and we put this out at 85, 90 intersections, somewhere in that range. Got those out there. I believe we're probably up to 110 or 120 here in Tuscaloosa now. So, and newer technologies also. When I started looking at this, I don't know if anyone will remember names like Savari, Arata. Coda might still be around, but they've been bought and sold. The first thing I was looking at was buying some Savari radios back in the day. And I realized I had sort of a panic moment where I said, if I place this order for 90 of these radios, it's up to me to figure out the integration to the actual traffic applications on this part. Radio manufacturers would be glad to sell you radios, but then what do you want to do with it, the application side? That's where we wanted to think a little bit farther. While we were going through all this, there was funding coming in also immediately once we got those radios hung. NSF funding, this was me working with some CS colleagues, Xiaoyan and Travis. I don't think they're on the call, but looking at some of the networks behind these vehicles that are moving out there that are connected. That poll on the right-hand side, I don't know if I should be proud or embarrassed, but really that's a project that Dr. B, if you see Bharat Balasubramanian on here, and also Josh Biddle, that was another DOE project that we were looking at sensing, radios, technology. So I'll point out our original DSRC radio, the next DSRC radio, the CV to X radio, a bunch of census repeaters and access points, and some radar and cameras. So this was a pretty cool project we're wrapping up right now. And so we've got a next go that I think that we're going to be starting soon, hopefully. One other mystery piece that was inside, and I'm guessing on this call, many of you will know more about this, is trying to get one controller of a particular type to talk to one radio of a particular type. So if you were using a Conalite, Siemens, Inalite, trying to talk to a Savari, Coda, or Arata, back in the day, there were a lot of issues trying to make that a smooth process. There was a piece that we found that fit in the middle, and there were a few other reasons that we went with this, but this was from a company called Applied Information. This was very early on. And so we ended up using this, what we called SPAT translator back in the day, that would sort of solve the matrix of trying to communicate from one component to another. It worked great, and we ended up using it for a ton of other variety of applications. So that was just one thing that it did. But talking with them, there you will see some use of 900 megahertz radios on some of these projects. What I've learned is that we need to think really about what information do we have, where do we want to move it, how do we want it to be used. It's been fun for me. I remember back in 2012 hearing about cloud computing and this nebulous term. And now everything in the past 5 years has shifted to edge computing, and it's done out on the edge. To me, it doesn't matter too much where you do your computing, assuming that you've got the right time on where you're getting this information that you value. But this part right here was meant to help a lot of this on the cabinet side, working with the controller to the radio. This is our platform. This is actually old now. This is the previous generation. The next generation was released at the end of last year. We went over to Atlanta to meet with the group. But around Tuscaloosa, this was cool for us. We deployed this, and if you drive through Tuscaloosa, please do download this app, Glance Travel Safely. It's free. There's one for iOS, one for Android. If you haven't seen some of those videos online and demos, you can get that, and you can drive through all of our intersections today with what you've got in your pocket and get this information. There are some OEMs that are coming online with this. I believe Audi and Ford are pretty well integrated now. So if you're driving one of those newer cars, we're starting to see those pop up on our system too. What is interesting to note is that even though we had DSRC and CV to X out there, we don't see a lot of vehicles out in the wild driving around with that technology. It was really still more of a test case on the applications that you might be after, which I'm going to come to in just a moment. There's one other mode that we use that's not so popular, but we've seen that it is actually more popular over in Europe, and I'll talk about a Germany trip that we went on earlier this year. that's including a cellular network in the model of connected vehicles. The lower part of this was that old style DSRC 5.9 gigahertz, 75 megahertz of spectrum. Hopefully many of you have played with these things. We had really bad luck with them. We had things overheat. We had to do a Bluetooth connection to an Android tablet for an HMI that would overheat after about 10 minutes. It didn't go so well for us, but we kept going, we kept trying, and the CV to X stuff is going better these days. The upper part is most interesting to me. Like I said, I'm not a radio engineer. I'm not an electrical engineer. I'm not a computer engineer. This up above was stuff that I could actually work with and get out there and start to do some actual testing out in the field. This is another great picture I took many years ago. Brian Mulligan, if you ever talk with him, there's a term that he used back in the day called radio wars. And so on the left-hand side, you'll see that OBU that's in the vehicle to some Android HMI that's there. You'll see CV to X with its HMI. And then the other side is the CV to N, which we sometimes term UU, as opposed to the PC5 CV to X. And that UU is something where we don't need to have the other components that are there. It actually does rely on cellular networks. Back in 2018, we did a study on there, and the latency was somewhere around 400 milliseconds at most. These days, it's down below 120 was the testing that we've done with T-Mobile that applied information is carried out. So the latency issue, if you are doing criticals, let's say truck platooning where they're following milliseconds apart, I would not want a cell network in that mix. But if you're doing SPAT, pedestrian messages, and things like that, you can probably use this to a lot of success to maybe 80 or 90% of the applications will work. This shows the actual behind the scenes data that we were getting. This is a UDP dump that we get of the packets that come in here. When we talk about basic safety messages, I have to see things and put my finger on it. So at the bottom, that second row and the bottom row, those are BSM, basic safety messages. What that was is us turning on our phone, driving out around in the field, going on buses. William Alexander and Xiaoyan Hong. William finished his PhD earlier this year at Texas. And he was a CS student working with me. So we were taking this data and looking at some transit priority, which is going to come full circle towards the end of this project or this talk today. We built upon this system. I mentioned I wanted to explain those first 5 slides or so to show you where this started. The start was to get a network going with modern controllers and data logging, but then we added to it with central systems, with our SPAT translator and our connected vehicle platform that we had, then adding out DSRC radios. I regret putting a Tesla in here. I think I put it for some flash back in the day. The Tesla didn't have any magic. And in fact, that DSRC is actually terrible because it did not have that technology. Really, the path that we followed was the blue arrows was pushing out over the cell network to some sort of device that was in the car there. So the purple arrow is a little misleading on that part. Ideally, that would have been adopted back in the day, but we never saw that happen. And so if I remember back, I think it was at Ajit Pai, and there was a whole bunch of chatter with FCC, and they reallocated that spectrum. And so a lot of stuff's changed since this was first deployed. The first time I saw this figure, I spent 45 minutes talking through it. So I can't spend that today with y'all. I loved it. I mentioned that we have to think about what information is where and how do we want it to flow. So whether we're out on some signal controller, how are we going to get it out to a device, a vehicle, an HMI, whatever that endpoint looks like? Are we going to go over CV to X? Are we going to go over the cell network like I mentioned through a mobile app? Are we taking in 900 megahertz EVP, TSP signals? So trying to think about where the information is, how we want it to flow, what paths it will go. Is each path viable? Is the latency going to be okay? Is the bandwidth okay? Those are all things I don't know, but it's fun to just go ahead and talk through these things on whiteboards and make sure that this is going to work when we go out to deploy this and do the testing. I'm going to try to mute this video. Hopefully that's an option here. But this is driving through the campus. You can see football tent set up there. So this was fall of 2018, I believe. I am going to pause this video just to point out just a little bit of sort of the struggle that I had and I still didn't fully understand. I'm going to pause right here. This phone. So first off, if you're a distracted driving person, that's not the intent of this. This is a temporary HMI solution until this information comes into the driver information cluster or maybe the some sort of infotainment platform. And it's really supposed to be auditory, non-visual, that we're leaving it alone. So we're not touching the phone, we're not interacting with it. But here's the part that just I never really rectified. Up on the pole, there is a DSRC radio. That DSRC radio is not doing anything in this particular video, nor at the next intersection or the following. Really, inside this cabinet right here, there is one of those edge processors that is going over a cell network. Ours is also backboned on fiber, but we can work with cell where that's how we're getting the information. And you'll see that in a slide later on here to just make sure that we talk about that path. So even though we wanted to make sure that we could say, yes, we officially have DSRC deployed, we are legitimate, I really think that we found a lot better traction working on the cell network side. Unfortunately, I wish it was more elegant and it was the open side. We are getting there with CV to X. That's encouraging for us, but we just really struggle with some of the hardware early on. So driving through the intersection on campus, we're getting signal status. You're going to see a get ready for green. And I'm guessing, I would estimate that hopefully 50% of the folks on this call have seen videos like this. There's a get ready for green. Hopefully the video is not too choppy on your end. I do want to try to come towards the end of this video where we approach this intersection and all of a sudden it looks like we're accelerating. So it does give us, oops, I'm sorry, I meant to pause that there. Let's see if I can pause. A red light warning. Sorry, where was I? Right about, oof, I'm close. I don't know if I'll get it on this now with the pause frame, but anyhow, the red light warning that we were after, that was an immediate safety application that we had running out at all these intersections in 2018. You did see some things like pedestrians run in front here. So this was us learning how to use this safely. I've had people give me feedback and say, hey, it doesn't give me the actual green time for when it's going to start. We give an approximation. The controllers are not deterministic in that way where we can just give you a time. We can say that there's 10 seconds at least until green or things like that. So the messaging and watching how users use this information, that was part of the study that we wanted to look into. This is really old. I did check the link down below. FHWA has updated this a little bit. But most of these have stayed around. The question is, once we put this in place, what did we want to do with it? And these were the applications that we were looking at. The green ones were ones that were deployed out there. So this was fun for us to see, there are drivers out there using this. There's pedestrians using this. It's fun when some people walk up to me and give me feedback on it and say, I'm glad to hear that you're using it, that you like it. And so lots of good applications that we had working on, again, a cell network side, which I used to be really embarrassed about. People used to make me feel ashamed on it. And that was okay. I'm proud of where it is today. So, but yeah, that was good. We did spend a lot of time though looking, and this was out in Fort Collins, Colorado, looking at here's yet another DSRC radio. A lot of this, I know that there's a lot of folks on this call who are experts in cybersecurity. I'm not. So that's something that I just want to be able to take for granted and get back to the traffic application. There are folks who a whole career study cybersecurity in the transportation systems, and that's critical. I would rely on folks like that to make sure that they're able to help and say, are these things safe, secure, protection that's all in place appropriately. So this is Tony English and his wife, and we went out there. We did some test driving. I'm going to come back on this DSRC one more time. Sorry if I'm a little sour on it. This was in Tony's neighborhood. We were in his Suburban. That's his Tesla in front. We had two OBUs, and in this distance here, what you're seeing on this HMI or maybe can't see is that it is not communicating with the vehicle in front of it. There was a lot of struggle with antenna design. In this particular vehicle, the Suburban, the roof was so large that was a problem, that we were trying to run these cables out the sunroof and make sure that there wasn't interference. Again, I'm not an antenna engineer or an electrical engineer. I was a frustrated traffic person that said, why can't this connected vehicle technology work? So this was just stuff that we continued to battle through. And so we went out to see the Wyoming, the official deployment, one of 3. I did go out to New York and talk with New York City on what they were doing. I have not been down to the Tampa one. I've driven through there. I've tried to ask Dave Miller from Siemens, but anyhow, this was us just trying to explore and see what we could come up with. I do want to make sure that we are moving forward with CV to X. And so this is a military project that I won't talk a lot about here, but we do have CV to X testing that's going on this campus. Matter of fact, last week I deployed 5 CV to X units here for an FTA transit project. So we have gotten involved. Zach Chaffin just finished his PhD, and then Dr. Nathan Zhang in electrical engineering, colleague also on the call, Dr. B. This has been a group that we've put together to make sure that we are still going after the official way to do things. But for me, at the end of the day, I'm still traffic. And as long as I get my traffic applications, I'm pretty happy. When we started doing connected vehicle technology, ALDOT came to us and they said, we want to think about how we want to use this. And so we talked and brainstormed. And their first way that they wanted to was interesting to me, is they said, we really want to use it for freight in this state. Alabama is a port state. Mobile, there's a lot of freight that comes in and out. There's a lot of freight along the river, the Black Warrior, the Tom Bigby, stuff coming along the I-65 corridor. So we had an issue, and this was kind of an impetus for this proposal here. We had a truck overturned. So this is a safety issue, a freight issue, an operations issue. We had to close down this stretch of road, and this was a major one of 3 routes through Tuscaloosa. So we routed everything onto McFarland. The only problem is there's 26 signals along there. And so we've gotten pretty good with our management center on that, but for some of the just-in-time, just-in-sequence routes that we have coming through here, we wanted to partner with industry and say, hey, when these situations happen, we don't want to disrupt what's going on. This was a great working relationship that the DOT maintains with local industry around here. You'll see ZF is a chassis supplier. Right-hand side over here out in Vance is Mercedes. Those are pretty critical supply chains that are big economic drivers in this city and in this county. So this work next that you're going to see, this is probably one of my favorite applications I've gotten to do since I've been here. Dr. Sufyan Talukder, he's down at AECOM in Florida. He was my first PhD, second PhD student, sorry. He graduated, I think 21, so he's been down there for a few years now. We started looking into how freight priority systems were done. Traditionally, we were doing some loops. On McFarland, we had some what are called system loops or discharge loops. And we saw that there were a lot of issues with that when we started looking at the ETAs of trucks arriving at the next intersection. So we wanted to come through this part. We were looking at connected vehicle technology to design a signal priority system that would improve on the traditional loop-based priority. The ETA stuff back in the day is what we were calling it. It's more morphed into what we call now NTCIP 1218. I've got another CS student, luckily, who came on board this semester, and we're working through taking in some of those objects and using the V2X hub to be able to translate and pull those apart. So, and the last bullet is probably my favorite, is we did a lot of field testing on this. And that's what I want to share. We learned more communication side stuff, which isn't what I was after, but we had to really kind of dig in and figure out what was going on. I will go quickly through these slides. Really what it is I'll just talk about a few of these things. We're trying to figure out the time of arrival that we would estimate based on some loop pulse that we would get. If you design for 50 miles an hour, you can place these loops appropriately at 50 seconds, 20 seconds, and then have checkout detectors. The truck coming through, if the truck is coming through at a design speed, everything works great. You're 50 seconds away from the intersection. We know what to do. The controller can start making calculations. We get a second check-in at 20 seconds. The controller updates its calculations. Hopefully the speed has been perfect. There's no variation at all. And hopefully everyone says, yeah, right. Of course there's going to be issues. So if I have a truck that's not going that speed, all of a sudden all my assumptions are wrong. And this really does have an impact on how the system works for itself and for other drivers. And I'll show you that in just a moment. But if we start to do some of these estimations that are wrong, that's where we'll run into issues where even though I think that truck's only 20 seconds away at 50 miles an hour, at 40 miles per hour, I'm 25 seconds away at that design speed. That's a problem. And so as we start to take a look at what this looks like, I'll show you some time-space diagrams. We changed. We did all of our stuff with ETA. This is through a proprietary system. We think that we're going to be able to do this through CV to X to do it in an open platform also. It's just new technology that's coming around, and that's what we're working towards on some of our FTA work with transit. Similar concept, different application. But this is showing, preempt ETAs, channel numbers coming into controllers, and we're going to have this externally managing and doing better information to get to the controller. I think there's a big gap that I see personally. I think I work with signal controllers quite a bit. I see a lot of research that gets done that's really good, but then the first question I have is how do you get that to a controller? How do you get that information in? Because remember, controllers only work on right now inputs such as, channel on, channel off, loop on, loop off. There's a metal object over a coil of wire. There's no metal object. So trying to work around some of those things, there's been applications that have done quite well with that. Adaptive systems, some of these priority systems too. NTCIP
Well,
12.
I had set it up for tomorrow.
Oh, Patrick, would you
Friday.
mind muting? Thanks. Um,
Yes, I had a lot going on this morning. I think I said Friday the 12th, but
I don't know, Caesar, are you able to mute Patrick? I'm not sure if he knows that he's unmuted. Okay, sorry, I'll continue here. I'm gonna do my best with time management.
thank you so much. I'm sorry for that confusion.
Hey, Patrick, are you there?
Thank you.
Can I right click and mute? Caesar, can you do anything or? Oh, well, okay, there we go. Sorry, y'all. Okay, so back on this part. What I wanted to show you, this is a diagram where we were able to look at the information that came in for each of those channels for the different check-ins and see what would be the implication if a vehicle was not following a design speed and an actual speed. So as we looked at this coming through here, there's a lot of animations and click on this part, but really what I want to show you is at the end of this, if we do a wrong prediction, we're going to miss it. Then there's really no point to this priority system at all. So when we started working with ETA-based systems to get better estimations on it, we could do a whole lot better. You can see that the information changes where instead of just being a pulse over a loop, this is more continuous information that we can get in there, that we can have logic statements to actually provide better, more accurate information of the vehicle and how it's moving. I'm going to step through a lot of these on the time management side here, and I'll show you the results on it, which is the exciting part. This is fun to talk through, but now that I look at it, I included too many slides. I was excited to share this part. But a lot of these things, trying to figure out how do we make decisions on either early return to green, extended green, are we going to hit the coordinated movement and be able to get through there without any disruption at all? This is the type of math that we had to dig in quite a bit and think through as we were designing this system. If you've worked with priority before, I'm sure that you've done these calculations and these setups and programmings, but for this was us going through. These errors on here that we did want to look at, I want to show you the actual part here. We started looking at the time of entry in a cycle. I think we were running 120-second cycles, what it looks like here. I think we're running 150 these days. But depending on the speed that you're going, the number of errors that you can make. If we're driving through the corridor at 50 miles an hour, we're not going to have any issues based on that design that we had. If we deviate to 49 or 51, we still have zero differences. But once we start to get more than a mile or two per hour outside of the design speed, all of a sudden we start to have a lot of errors, which would cause wrong things to happen. Either a truck is going to have to slam on a brake at a very bad spot, or they're going through a signal that they don't want to, or there's an extended delay that they're going to have because we made a wrong call on the priority. I'm going to show you some of the exciting stuff, and really the final result of the video is the best part that you'll see. This is still just quantifying the errors. I'm trying to take a look at if we deviate at all from the design speed, what does that have for ramifications for what that would be on poor operations. We tested this on the northern part of the corridor, only 13 of the 26 intersections. This is north of the river. There's a pretty good logical break. South of the river, there's an adaptive system that I won't bring up today or anything, but this 13 intersection was a great test bed for us. This was us driving through. Again, there were two modes of communication. I think I've got a little infographic to show you. Truck coming through the intersection can communicate either directly to the intersection within about 1,000 feet. If you're an electrical engineer, you will not believe that, and that's fine. We'd have to do some sort of packet error rate or some sort of signal loss test. Nominally, we say about 1,000 feet, we can start to get to the intersection. I'll show you what that looks like. However, if we can't communicate at that distance, we can also go over the network side, CV to N, to bring it into the cabinet that way with the other component that we installed that I mentioned. So this is a very simplified graphic of how it's supposed to work, and it did work. But we did find instances where these communication paths would drop out, and then we'd have to figure out, do we have a redundancy that we can go over? We spent a lot of time watching the controller make decisions. This was running an old version of CPAC. I don't think we were on the 5 dot yet. I think this was back in the 4-dot days, and actually the 3-dot days for the CPAC side. But these are all the controllers. LDOT let us log in, be able to watch the decision-making process of these controllers. We had a lot of information on logs coming through. Those logs are what we were using to check to see, did we get cell communication? Did we get both? Did we only get radio? What was the time that we received, the check-in times for different distances here? So we would give ETAs on this part, be able to watch all this. There's a lot of parsing this out here and getting this into some digestible results. We also paired this with, like I said, our backbone ATSPM data. We had great signal data that we were recording. Putting all of that together, here's a very, very important slide. We did multiple different test drives on this one, starting in April, going through May, and we were looking at how do we drive through these 13 intersections? How did comm go? Did we catch the green band? Did we have to early return to green? Did we have to do an extended green? And so there were all sorts of different operations that we were looking at. Some of our base runs were up in the 13 to 14, even 15-minute range. When we were running with full communications, we were getting down to 8 and 9, really in that range, making it perfectly through the corridor without stops. It was really cool for us to see that. That represents about, when we actually quantified it for the paper, that you'll see about a 47% improvement at best. So this was big for us. We were excited about this. This was something that we could go ahead and put on trucks, probably conditionally. We didn't just want to give them the green light all the time. I've had people ask me, well, are you going to start selling green time to pizza delivery companies? And the answer is no. That's where the working with a partnership through the DOT and the private side is we want to figure out when is it appropriate? How do we do that effectively? We've actually got another DOE proposal that we've worked on that I think hopefully we'll be able to expand upon that topic. But this is just showing time-space diagram going through the corridor where we did get something like a green extension or an early return to green to try to get that truck rolling as quickly as possible. This really exciting result on this first row is we came up to one of the larger intersections, US 43. This showed our system working perfectly as we designed it. The early estimations were that we were going to go through on the coordinated green band, chord. On the very last check, and it said, hey, you're not going to make it on chord. You slowed down. We are going to have to extend green. So they made that decision and it worked perfectly for us. So all these decisions, whether it was extended green, early return to green, we worked really smoothly and it was really fun to go through this. I probably won't show this whole video. It's on my YouTube channel. We were able to drive end to end on this corridor without stops multiple times. This is one that we documented in detail where we're watching every controller front panel. We're watching the information flow in on all the 50, 40, 30, 20-second check-ins on the ETAs. So coming through, there's two spots where this one got a little sticky, but truly, I mean, when you take a look at the time-space diagram, I'm going to fast forward to some of the latter part of this. Chord green, we made it through there. I think we're going to come up priority green extension, chord green, come up this hill, which is actually a challenge for the trucks. That's another thing for us to consider as we're looking at some of the geography, priority green extension. And so as you look at this time-space diagram, I'm going to try to pause it at the end here. This is one of our perfect runs. I think this was the 8.5-minute run that we made it through all of these intersections. The last one will be coming up. But that right there was the improvement that we were able to make on that part. There is a lot of truth to say that if you have good coordination, you'll make it a lot of the way, but the trucks have a lot of different dynamics. And so that's other parts that we're able to factor in and take a look at how they're driving through these systems. So like I mentioned, this is probably one of my favorite applications here. With the remaining time, I do want to shift gears a little bit into some of the more trajectory-based control, which is what I was interested in. When we talked with LDOT, their number one was the freight priority. Our number one was saying, how do we get BSMs into a controller so that we're doing call, extend, delay measurement, and we're trying to optimize that way and run a controller differently instead of just using traditional loop calls. I borrowed this picture from Mark Taylor. I love this picture. If you're using just traditional detection, an intersection doesn't see a very good picture of what's happening. All it looks at is either squares, coils of loops, zones, whatever you want to call it, to say there either is an object or there is not an object in here. It's not a very high resolution picture. And so this is old fashioned loop detection that's out there that we're all used to. but we want to try to figure out how to get those basic safety messages or trajectory information into controllers. This is really cheesy. We started off in simulation. It was a good start for us, but I'm going to show you where we got this to full-scale deployment out in the field. This is an intersection on campus. This was students learning how to work with a comm interface to be able to look at vehicle trajectories in simulation. I'm guessing many of you have dug through these files as you're doing some of this testing. For us, we were just trying to come up with some simple logic. This one was really cheesy, where we waited for 3 vehicles to be stopped and then we would change. It actually was quite effective, but it's not the best logic. And there were so many applications or algorithms that we went through to try to take a look at how could we improve over just running free at this little intersection we have on campus. Ultimately, this led to a paper that we had in ASCE where we were measuring delay. The delay is what we ended up using as our measure to be able to reduce and optimize for this intersection. So we were so excited when we got this paper done, and this was probably about 2019. I think the publication was in 21 after Sufyan finished up his dissertation there. But we had this thing going along. We said, how are we actually going to do this out in the field? How can we measure delay? So I was at TRB, I was at the vendor hall, and I talked with Brian Griggs from Econolite, and he said, hey, we have a new radar system that's going to measure trajectories from every vehicle. From there, we're going to turn those into objects and be able to use that for delay calculations inside the controller. Now, if you know about traffic signal controllers, they are not the most powerful computing units that are out there. The Cobalt, if I got this correctly, I think it's a 625 megahertz processor, which is, I think, the most powerful one that was out there at the time. The Siemens, the old controllers, were down there at 25 megahertz running OS 9. They didn't have a lot of calculation or capability for computation. So on this, we actually got a prototype project or product here. The folks in Tennessee use these a lot from what I understand. This is a connected vehicle coprocessor. It's a secondary computer that goes inside of the controller that's able to do, if you want to call it edge computing or whatever, that's fine there. But it's doing that computation on this card, interfacing with the signal controller through their platform that was called Sky back in the day. So we were testing on this one. This was fun to go out there. This was 2019. It was pretty cold in Alabama. It was probably like 50 degrees. That's a joke, kind of. But we got this thing out there, put it in the controller, and we ran this for a bit. And I'll mute it on this part. This was fun for us. This was actually seeing an intersection from an overhead view with these trajectories to see where vehicles were placed on this map. How are they approaching? How are they arriving? How are they departing? And with the object list that you see in the bottom of this video, we could really start to take a look at delay and calculate and keep a tally of that so that we could say, hey, this approach is the one that's accumulating the most. This one's predicted to accumulate the most. So there we can go on that part. I do see some questions rolling in. I'm going to keep going off here because I fear time's going to work against me. Just to show you a pretty good snapshot around February of 2020, this was when we got everything working together, lined up. I'm going to come forward just a little bit in this video where you can see me and my car getting connected vehicle information, SPAD information from the cabinet, the radar's tracking my car coming in. The radar has me as an object. I also have my BSM coming in on my connected vehicle platform. So this was everything glued together. Safety applications. This was quite a chunk and quite a good milestone for us to hit, especially right before the pandemic happened there. But that's probably the snapshot of where we got to on connected vehicle. Like I mentioned, the flow of information, it's really fun to think about where all this stuff's going. What are we sharing? Who needs it? Does a controller need it? Does a driver need it? Does something else need it? Even powertrain, we're trying to think about that. Can we get it to a vehicle that can make a decision on what to do as far as idling or shifting or whatever? This continues to evolve. The last part of this presentation, and I'm just keeping an eye on time to be careful here. I'm going to try to end by 50, 55, somewhere in that range. But as we take a look, this evolved into what's now the Econolite Evo. Hopefully many people have heard of this platform that's out there. This is a pretty intense radar system that's able to go out and get even better data than we were seeing with the AccuScan or the Smart Micro platform that was under Sky. This is showing that same intersection. So again, we're getting connected vehicle data coming in. I say connected vehicle data. I want to be careful. I should probably take those words back. We are using this as sort of a surrogate or temporary placeholder for connected vehicle data. I think / hope as I'm sure many of you do, that in the future, we will have that more readily available. I'm glad I'm a traffic signal person. I'm not a planning person. I don't need to track you from your work to home trip. I don't want to know anything like that. I just want to say, if you're within a quarter mile of an intersection or 1,000 feet or whatever that distance is, how can we safely and efficiently keep all that traffic within that bubble distance going through the intersection as best we can? Best is one of those words that I understand, safety or operations or efficiency. We can talk about all of those things, but that's really what we were after. So when I say connected vehicle data, it's really trajectory data from vehicles. If I get it from a radio, fine. If I get it from an infrastructure sensor, fine. This was another glimpse that we had. This was WEJO data from back in the day. I'm sure everyone's heard of this now. I think in the future, TMCs will have maps with every vehicles on there. I'm seeing that at least in one central system and another central system. So it's coming now where a lot of our central systems, we run a Centrac system. It's great to see the green, yellow, reds, but what's missing, unfortunately, is the vehicles. But with the detection systems, we can actually get the vehicles placed on there. So that's, I think in the next 5 years or so, that's gonna be pretty common that either a camera or a radar or a LiDAR will place vehicles so we can see where those cues are and how vehicles are operating. So WEJO data, there's a whole other talk. I'm not trying to get into that one today. We are getting smarter. This is actually an older video, I think. I forgot when it exactly was. We've got a second generation of this now. But watching vehicles arrive, this is a platform that once that vehicle comes, and you can see there's a little bit of an issue. We've actually tuned this quite a bit now. Once it drops down below a certain speed threshold, we actually watch the wait time for every vehicle. So we're no longer trying to do counts to go to the highway capacity manual to model delay. We're just going to watch every single vehicle and see how they're accumulating time. So this was on a single approach that we were testing on. We now have a quad or 4 approach system that we're looking at. And so we get down here in this lower table, we get reports on what is the measured delay that's at this intersection. This will absolutely be coming around. There's no reason for us to do count data to model to get delay. We're in the age now where we can just measure delay. And when we get to connected vehicles, we'll truly be able to see whatever delay they're reporting. This same intersection, if the camera wasn't convincing enough, this LiDAR system that we've got, this is a fused 3 LiDAR system from Soul Robotics. We're actually deploying the 2nd gen coming up this month too. This was from about 2 years ago. So this one will get the upgraded one. I'm going with a blue band platform to be able to do even more measurement of all sorts of things. I do love this video in particular because as class lets out, this is a huge classroom building here at the university. You can see the students flood out through here. So when we want to start to think about safety with vehicles, pedestrians, cyclists, this is a detection or sensor system that will allow us to do that. So this is our latest, most exciting one, I'd say, but there's some camera systems that are just incredible too. I like the ride share where folks are getting picked up. So now we can take a look at different types of trips. Here comes a cyclist or a little e-bike that's zipping right through. So all sorts of micro mobility, shared mobility. These sensor systems are really opening up some cool insights for us. I'll skip this one because this is probably just pairing them together. Last few notes I've got, just a few other projects that we're working on. Over the summer, yes, Alex, go out and sweat and change 7 cabinets to ATC cabinets. This is a brand new intersection, but we had 6 other intersections that I manage and operate. And we did new 32 channel ATC cabinets. I learned a ton on ATC. I don't know if Ayrton's on this part. Ayrton is like the best signal person that's out there for training on it. I had never been trained up on ATC. So if you have any ATC questions, there were a lot of lessons learned on SIU, BIU, trying to figure all that and sort it. So these are camera systems that we've got on campus now. This is a new Iteris Apex. This was the first 1080p video detection platform that I could find. Working with folks like Nader and Allison to hopefully get more ML applications on it. We want to get a lot more data coming out of this. And this is stuff we have live that we're able to pull from. Students will work with, and that's fun to be able to share these feeds. So that way they can do more testing and whatever they want to try to deploy. Digital twin, back to that WEJO concept. This is our new quad intersection that we had, that we were getting up. And so we are from camera starting to do some sort of digital twin live model to see where vehicles are. It looks like it's the middle of the night, but I think it was just winter at this 5:38 time. So I was out doing a presentation. This is at the opposite approach, but here comes two cars towards the camera, and you can see them roll right on through here. So this, I didn't think I'd see this for quite some time, but to be able to take trajectories and vehicle location information from a video and put it on a map, this is what I mean by in the future, this will be in the central systems. I think it's gonna be sooner than 5 years, but 5 is a safe bet. Last part here, I think I'm gonna be pretty good on time. We do have some other these large applications. This has been a fun freeway arterials. I'm working on an ATC MTD project. I don't know if Elsa's on the call, but there's been others who've been worked and involved with this. This is a freeway stretch that we're trying to, the Tennessee folks win with the I-24 corridor. I get that part. For us though, on this rural suburban application, we said, what can we do to help our traffic management center with freeways, with, parallel corridors and routes that are on this. So this has been a good project. We've got our traffic management center now equipped, watching this, managing it. We're working on the evaluation report for this project. We were really proud of this. This was kind of cool. I got asked to go out to New Mexico to talk at an ITS America thing. They popped this map up there, and we were the only university listed on that part. So yes, there's other university involvement in many of these projects. Ours was very different where we were leading that project. I look at this map every time I pull it up to make sure I'm not lying that there's not other universities. I thought there was one, but anyhow, we've done quite a bit with Federal Highway working on these types of projects. I'll skip over this, which is the actual deployment itself. This was fun. I got home from spring break and I was like, oh my gosh, they're boring in conduit. So I jumped out of the car, grabbed this picture, jumped back in, and that's a pretty typical event for my family. The next one that's coming up, we're going to work on this through 2027, is we do have another ATC MTD project, similar, but we're going to do more freight management priority, connected vehicle stuff going through the city of Cullman, Alabama. It's a very mountainous, for Alabama, terrain. That's tough for us to manage, lots of weather, lots of crashes and incidents. And so similar ITS, ATC, MTD deployment that we're doing there. I did want to pull this up here. Our pole spacing, camera spacing is probably on the order of a mile or so, unfortunately, that suburban rural. This is a fun picture where Dr. B and Josh and I and Dr. Jones, we went over to Germany in May and we saw the German equivalent of this where they had camera spacing every 100 meters. I wish we had the money for that density, but we did the best we could. And so I'm still making progress. But all that said, lots of hard work, lots of cool projects, sensing, connected vehicles, intersections, freeways, transit, freight. This is a somewhat of a summary slide here, just of some of the flavors that I gave you today. The team effort behind this is extremely important to me. I just keep writing emails and asking questions and making a mess of things, and everyone else helps to make it actually work and come together. So this has been fun working, city, vendors, the DOT, consultants, other folks from the university. And then the other part is not just the research aspect of this, but the teaching side. My colleagues, Dr. Liu, Dr. Rahman, Dr. Jones too, our students through our program here, Civil Construction Environmental Engineering, I was estimating that we probably have about 200 students a year coming through in some sort of transportation course, whether it's our intro course. I teach roadway, I teach traffic, Dr. Liu does planning, Dr. Rahman does safety and also traffic flow. So we have quite a few students coming through. And so this is what I'll end on here, just to kind of show this was me with my class about 2 weeks ago. We were doing the CV to X installs at one of our new ATC cabinets. And that's something that I'm proud that we get our undergrads out there to be able to see. So cool, fun stuff there. I'm happy to take questions. My website's alexhainen.com. Please feel free to reach out via email. I'm probably going to share one more video in the chat here if it's still on my buff. Yeah, it is. So that's just a recent video that highlights a few more things that are going on around here. So I think I hit my time. No one told me. Oh, I hit it like on the second. It is 11:55. I think I got 5 minutes for questions, but I'll turn it back over to Caesar for whatever that we have. So I'll leave it on this video, but that's it. Thanks, everyone.
Alex, thank you. I hope everybody understands now what I said about Alex's love, affinity for traffic engineering. Just real quickly, there's one question that popped up in the chat there. I don't know if you can see it, Alex. on how does the algorithm adjust when there are multiple freight items with different speeds, including outliers and unexpected speeds. So that would be the freight priority corridor.
Yeah, this is always, we call these edge cases when we get to things like this. We like to start with the simple cases. So that one intersection I showed you on campus, I'll go back and talk about that for a moment. I like to start with a simple intersection to get the concept working. And then we do think about those things and we'll build and adjust and account for it. So great question on that. We were just doing the concept testing to get that going. In the future, on next stages, next future work, we'd want to start to look at that. And we are going to have that issue popping up on some of our future tests that we're looking at, whether it's transit or freight. So great question on that. We were really looking at some of just the first application to see, will it work? Yes, it did. But now that is an excellent example of something to say, how are we going to account for an issue with multiple vehicles, multiple directions? And so it's really up to the end user on that part as you set it up and configure, but it's a lot of discussions on that. So
excellent, excellent. Saeed, you have your hand up for a question.
So, thank you for bringing up the I-24 smart corridor with the connected service deployment. I'm proud to be part of that deployment. Was mentioned that there is the I-24 motion project, which is every time it's 44 poles, about 280 cameras, but it's deployed on the interstate and it's monitoring trajectories. And the data is
Saeed, I don't know that I can hear you really at all.
Yeah.
The microphone, yeah, it can. Jones, are you confirming that you can't make sense?
Yeah, Saeed, sorry about, I'm sorry to interrupt, but something, your audio is not clear at all.
Can you hear me now?
Not really.
It's we can hear you, it's just very muffled.
Okay. Well, I'm trying to get closer to the microphone.
Oh, that's way better. Okay.
So I just wanted to bring up, there is the I-24 motion project.
Yes.
It's deployed over the I-24 smart corridor, and it provides the trajectory for traffic flow on that section of the interstate.
Yes.
Yeah, so that's available for research, and the intent of TDOT when this was deployed to make it available for any interest in the technology or testing applications and how it affects traffic. The only difference here that it's not on the traffic signal side, it's on the interstate side.
Yeah, we do balance both. We have a corridor that runs parallel to both of our freeway segments there. So we try to balance back and forth between that part. I'm really I consider myself a signals guy first and foremost. The freeway applications, it's great. That I-24 project, nothing but respect for that. I did a talk with Matt D'Angelo a few years ago at one of the GRITS meetings, I think, or also SASHDO. So yeah, similar projects, but the magnitude of I-24, that is incredible. When I looked at those test sets and everything, yes, nothing but respect for that part. So for us here, we're proud of what we've got, but yeah, it definitely is dwarfed by the I-24 effort. So congratulations to you all on that. It's really a huge nationwide, everyone knows about that.
Excellent, excellent. Let's see, any last minute quick questions?
I see 30 minutes left on the call, so I was told an hour or so, or 50 minutes, so I think I was close.
Yeah, hey, Alex, you were perfect. You were perfect. That was excellent. The and this was a great, just for my CR2 C2 comrades, this was a great start. At the height of this, we had 114 people on this seminar. Fantastic. Alex has dropped a couple of videos in there. He mentioned his website, alexhainen.com. I've dropped that in the chat as well. Please reach out to Alex. Reach out to me if you're interested in other things at the University of Alabama. And please reach out to Ali and Caesar about general CR2, C2 projects and initiatives that are going on throughout the whole Southeast region. Thanks, everyone. Ali, Caesar, do you need to say anything to sign off?
Just great. Thank you, Alex. It was really great talk, and thank you everybody joining today's. It was really fantastic talk.
Excellent.
Thanks, everyone.
Thank
Good
you.
Thursday, everyone else. See you soon.